the, I think easily the most challenging unit of the course. So congratulations. And I think it ends with a real doozy of a question, which again is going to show up. It shows up on your problem set for sure, and perhaps on a test or an exam. So, but let's get to it. So first, the question is, and the lesson is called, what is an amp? Well, here's this awful, and here's the definition. And I'm sorry, it sucks. We learned in grade 11 it was something that made more sense, but this is actually how an amp got got defined. It's the current, and this is all based on the experimentation by Andre Ampere. Okay, so imagine you've got two conductors. So these are both conductors that are sort of pointing into the page, right? So they're long, and they're long, rods pointing into the page, and they each have a current. But we're saying it's the current in each, so they're going to be the same. And if the definition of an amp is that if you had those conductors in a vacuum, which really means that the permeability of free space, the mu naught, is what it is. We assume it to be what it is in air, but it's actually, that's a bit of an approximation in air. It's true for a vacuum. Anyways, so you say you got two conductors that are 1 meter apart, and an amp is by definition the amount of current flowing in each of them if the magnetic force is 2 times 10 to the negative 7 newtons. And that is the definition of an amp. So if you're going to measure, say, the magnetic force on this one due to this one, it would be 2 times 10 to the negative 7. Okay? And that means they're both carrying an amp, assuming they're both carrying the same current. And that's an amp, as lovely as that is. And that really, then that progresses to the idea of what, we use in grade 11. I much prefer this definition. You can picture this. It makes sense. 1 amp is that many electrons in a conductor per second, right? That's how we see it, but this is where it came from. Okay? So this allows us to develop an equation, and it's only an equation that's relevant if you have parallel conductors. Okay, so this equation we're going to write down has a very limited application, but it is what it is. Smart people know how to use it, so you get to be smart too. So imagine you've got two conductors. This one is carrying I1. And remember, the dot means it's coming out of the page towards us, and this is carrying I2, again, out of the page towards us. And if you recall the left-hand rule for a straight conductor, first of all, that they're each going to create, each of these are going to create a magnetic field that's circular, okay? And using the left-hand rule, your thumb would follow the current, and your fingers would follow the path of the magnetic field. So that means that's supposed to be an arrow pointing up, because on that side of the conductor it's pointing up, and over here it'll be pointing down. So it would be a clockwise, I guess. Okay? So the idea with the equation is if I said the magnetic force on 1 due to 2, so I'm calling it FM1, and what I'm saying is, what force does this conductor feel or experience because of this conductor, because of the current, the magnetic field created by this conductor? That's what I'm saying. So there's a magnetic field here, but if I sort of kept drawing circles, the magnetic field here would eventually, it would collide with the magnetic field on this one. But, this one is sitting inside this one's magnetic field, right? So we learned this equation a couple of days ago. Just quick, I'm going to scroll back a bunch of pages. Magnetic field. Look at all this good hard work you guys have done. Magnetic force on conductors. Yeah, here it is. Right? Oh, whoops. Here, this equation. So this is the equation I'm talking about. This is if you place a current carrying conductor inside a magnetic field, it will experience a force, right? And that's what I'm talking about. The force on the first conductor that it's going to feel due to the field created by the second conductor. Okay, so here's the equation. And so I would be the current flowing through I1, right? This would be the current. L is the length of the conductors. Okay, B is the magnetic field right here due to this one. So we can find that using Ampere's law, okay? And then sine theta, it's, see, the magnetic field is perpendicular to the current because it's up and the current's into the page, so sine theta is just 1, okay? So from Ampere's law, we know this equation, so I'm going to replace B with this. And just quickly, if you're not sure why I1, I2. So I1 here refers to this one because it's the force on this one. This one's I2 because it's the magnetic field right here due to this one. Okay? So you sub in, and here, write this equation down. This equation's got to go on your sheet. In the specific instant of two parallel conductors carrying, one carries current 1, one carries current 2. Okay? So this has got to go on your formula sheet. That's a beauty. So let's use that formula a couple times. So two parallel straight conductors. This is the only case where that formula applies. They're 5 meters in length, so that's our L, and 12 centimeters apart, so that's our R, are to have equal current. So I1 will equal I2, right? The force each conductor experiences from the other has to be less than, so we'll use this case. We'll use force is equal to this, 0.02. So then what is the maximum possible current? So when we're talking about maximum possible, that's assuming that because we can't have a force any bigger than this, so we'll use that as our force, and that'll give us the maximum possible current. Okay, so we're looking for I. So it's just this formula, rearranging for I. Because I1 and I2 are the same, it becomes I squared, right? And get I by itself. It's a couple of big steps, but you guys are good at rearranging equations by now to get I by itself. And substitute in, solve. You can try it or trust me. 49 amps, which I check mark with reservation because that's a huge current, by the way. That's a big current, 49 amps. But that is the answer. Okay, so that's one example. This next one I think of as a doozy. It's kind of a goal of mine to make a lab out of this, but you guys won't have to suffer through that. Here she is. It's actually a combination, a lot what you did with your Coulomb's Law lab. Because look at this. This is, you've got two conductors, and it's very similar to the Coulomb's Law lab, except for they're running a current, and they're running a current in opposite directions. And so imagine, we could do this in the lab, though I haven't done it yet, but I send a current through each of these conductors going in opposite directions. And they're the same current, but just opposite directions. And then, they would repel each other due to the magnetic force between them, right? And then you would end up with a nice picture like this, and you could solve for the current or something like that. In this case, I think it's current. Yeah, calculate the current in each conductor, right? Because if you know the mass of the little conductors and you know the length of them, you can apply the formulas, and you can combine this with what we did in the Coulomb's Law. Okay? So we're going to use the free body diagram and gravity to determine magnetic force and use that in the equation we just learned for current. Okay? So, very similar to the Coulomb's Law lab, right? First we're going to find R, just being the center to center distance. So looking at it head on, right? It's just a cosine law. All right? And then do a free body diagram. And this is exactly like you did in your Coulomb's Law lab, right? We're looking to find the tension in the string holding up on that conductor. So we're looking at the conductor face on. Well, Fty is equal to Fg. So you can find your Fty. Okay? And using trigonometry, then we can find Ftx. Okay, pause if you need to, because I'm just going to keep going. Okay? There's Ftx. And the idea is that if you look at the x direction, I'm just going to jump. Ftx must be equal to the magnetic force. It's the magnetic force pushing them apart, right? So if Ftx is equal to magnetic force, then you can say, okay, there's Fm. And then we can plug that into this formula and solve for I. So it's a lot of steps. Got to be really smart to do it, but I think you all are. Shouldn't be too bad. Solve, big rearranging. Looks awful, but you can do it because you're smart. and you get, I'm check marking it again with reservation because that's a huge current. I'm checking marking because I know I did it right. I've done this question enough times to know. But it's a huge current. 229 is massive. If that went through your heart, you'd be dead. Like you need about 0.2 to kill you if it went through your heart. So this is a huge current. Don't send that through your heart. Anyway, that's the question. It's a tough one. I think it was one of the hardest ones in the course. Okay, but that's it. That's all I can't make it any harder. That's it. Have fun.